Ready to go? Cool. Hello, everyone. My name is Sasha. We can keep this like super informal. You can stop me at any point. I have a lot of slides. Some of them more interesting than others. You're very welcome to ask questions. I have a few slides on Boundless. I don't have as many on Boundless as I would like, but we do have an event on Boundless tomorrow. Please feel free to talk to me if you haven't got a registration. I'll get you signed up. Cool. Cool. So everyone familiar with Risk Zero? Pretty much everyone? Yeah?
On that side for sure, I don't know.
Yeah. Cool. All right. Well, that saves me some work. So Risk Zero, I'm the DevRel at Risk Zero, and Boundless is kind of like a new product from Risk Zero. It's in fact been separated a little bit, so it's a new brand. This is a protocol, a ZK protocol. How much do you know about Boundless? Probably not very much, right? I imagine. You know the name, right?
That's centralized bonsai.
Okay, good. You even know bonsai. That's excellent. Kind of, but actually, Boundless comes up in many different facets. So I'll explain now. You might need to push me through. You can click it. Yeah, cool. So Risk Zero with ZK proofs and the ZK VM, they pioneered that space. They realized in a couple of different things, like it's great to have ZK VM, and it's great to be able to produce proofs of stuff, and it's great to be able to verify them. But that doesn't really solve problems in blockchains in the sense of blockchains are still very slow by modern standards. Of course, they've got a lot better. They do a lot of re-execution. So what does that mean? It means like, hey, we've got 1 million ETH validators, and the one that's chosen is going to be the slowest node. We have to all wait for it to be catch up and do the execution to make sure everything's all right. And that's a lot of underutilized capacity in the network of Ethereum, right? There's a lot of computers. Actually, if we add them up in parallel, in series instead of parallel, that'd be much better. So unfortunately, blockchains have very simple computations. You can do a little bit more complicated these days, but still it's nothing extra fancy compared to what you have in Web 2 in terms of computations that you can actually calculate. Put me on the next one. Oops. Okay, it's working now. Yeah. So Risk Zero has always said that the solution is ZK proofs. So how do we scale blockchains is ZK proofs. I think a lot of people are moving towards that now in the space to understand that actually that's probably a good way of doing it. So now instead of re-executing a lot of stuff, we're going to actually do what's called proof of execution. And universal verifiability is useful in the sense of you generate a ZK proof period, a Groth16 or a Stark or a Snark, whatever, and as long as you have a verifier on that blockchain, you can go ahead and verify that proof. So now instead of being, the execution, we move from execution scarcity to what Boundless calls execution abundance. So Boundless has a few different marketing terms here. You're free to ask me more questions and we can go through the docs afterwards. But Boundless aims to be a couple of things, and to put it down into a few words, we have universal, unrestricted, and open. So universal obviously means that Boundless tries to work with as many blockchains as possible. The blockchains obviously have to have some ability to verify a proof, but we do work with Bitcoin a lot, so Bitcoin layer 2s, and they'll be using Boundless as well. So there's some interesting research being done there. In terms of unrestricted, as I mentioned, we're trying to basically offload as much execution as we can somewhere, even if they're untrusted. Through the magic of ZK proofs, we can now trust them, carry out some sort of execution and verify them, and have that kind of be put back on chain. And finally, we have, the idea is that for it to be an open ecosystem, it's a protocol, we call it the Universal ZK protocol, right? So actually, it's not just the decentralized bonsai, but that is currently the main aspect of it. So if you're familiar with I know the vlayer is definitely familiar with Steel, but if you're familiar with the ZK VM, you might be familiar with some of the other offerings we have. So these are built by Risk Zero. It's Steel, Kailua, and Blobstream Zero. And these, obviously, vlayer here in Aragon. So these are extensions to Boundless in the sense of Boundless is this protocol, and we have these ideas of extensions. Some of them are very specific. Kailua is, in fact, a roll-up stack. You can think of it as that. So it's kind of like a hybrid OPE-ZK roll-up stack that allows you to build a new chain with kind of the best of both worlds. Blobstream Zero, built in-house by Risk Zero, is a Celestia application with Risk Zero ZK VM for modular DA for your application. And today I've got a lot more slides on Steel. Is anyone actually familiar with Steel? Is anyone familiar with Steel? A little bit? Do you know how it works in general? A little bit? You do pretty well? Okay. All right. Because most of the rest of my slides are about Steel. So if you find that boring, you can tell me we can talk about something else. But
Let's talk about it so everybody else.
Yeah, sure. Okay. I mean, I go through like how
Vlayer is kind of inspired by
Steel. Yeah, that's why I understand. Yeah. And that's why I was asking. Cool. So the core services of Boundless, we have proving. So the idea of Boundless is that, okay, we have applications that want proofs. How do we actually get them proofs? Proving is expensive at the moment-ish. You need GPUs most of the time. Zero ZK's VM, which is at the core of Boundless at the moment, is GPU optimized. So we need to link people who have GPUs with people who want to request proofs in the market. It's kind of like a decentralized bonsai, as you said. Settlement in the sense of that you can actually go and Boundless is going to work with many different chains out of the box. And finally, we have aggregation as part of Boundless. Though to be fair, I think within RIS0 we've understood that proving costs are basically going to be, we're not going to talk about proving costs anymore, probably within a year or so. It's going to be so cheap that, yeah, for us at RIS0, definitely, I think the market is heading that way. Yeah, you can talk to me afterwards when I'm not on camera about that. So we do have an inbuilt aggregation. So basically, like, you know, if there's 100 proofs coming through, they'll all be batched and yours will be one of those. And when you prove the proof, you'll be certain that when you verify the proof, you'll be certain that your proof is done and it'll be 100 times cheaper or whatever. That's inherent. But you can also request a single GOS16 if you want. Some people, like in Bitcoin, people like that a lot. Next slide. Oh, we skipped one. Go back. Next. That's good enough. Yeah. So, I mean, I've already mentioned this. We have nice marketing animation of all the different types of chains. But the reason I actually have this slide up is that, like, before the ZKVM, it was pretty complicated. I mean, you can still obviously write your own circuits and do your own things. And I'm sure many of you are familiar with that. It's just a pain in the ass and requires a lot of effort and understanding, which is actually like very interesting academically, and the circuits aren't going to go away, right? But in the sense of the ZKVM that RIS0 pioneered is much, I mean, in some aspects simpler, but it's still not the most simple way of writing proofs. At the end of the day, what Boundless is aiming for is kind of a tech stack that like adds ZK to pretty much any application or a chain. So I think that's kind of the idea. Yep, next slide. Sorry, I don't think mine's working. Cool. There was two more. That was Kailu and Blockchain Zero, but today I'm going to talk about Steel a little bit. So the reason I'm actually going to talk about Steel, and I realize that vlayer, I imagine that there might be a few. I'm going to leave this here, by the way, because I don't think it's working. So yeah, please stop me if you know too much, but a couple of you probably were still interested in Steel. I used to be a Solidity developer mostly, so I find Steel very interesting and the aspect of Steel. So let's get started. I'll talk about Steel, one of the Boundless extensions. So the first question, instead of asking like what is Steel, I also like doing this. Lots of people introduce their new, I don't know, product, always saying like what is it. I actually would say that if you guys are all hackers, right? If you make a product, it's actually more interesting to start with why, and then what, right? Like why have you made that product as opposed to what it does. I think people usually are more interested in that sense if you start with that. So what does Steel unlock? There is RIS0 ZKVM, allows you to write Rust code, and you basically generate a ZK proof of that Rust code, and you do something with that on chain. Now, that's great, but it's still pretty generic. Like it doesn't, you still have to build a lot of stuff yourself, and especially you have to build a lot of stuff yourself when it comes to interacting with the blockchain. The RIS0 ZKVM has no network access, has limited memory, and so how are you meant to interact with the blockchain in that ZK proof? It's quite difficult. There are ways of doing it, and I'll get into how that works exactly. But thankfully, the RIS0 developers realized that we can't leave all these developers having to do this all by hand, so they built a library for it called Steel. So Steel is basically like the Ethereum and EVM blockchain interaction library for the RISC-0 ZKVM. Okay, so what does it unlock? Well, we have, I mean, it's public now, thankfully. So EigenLayer uses Steel. They are working to do they're doing a lot of calculations to do with balances on L1. Obviously, EigenLayer have a lot of money, so it's okay. But I mean, they still want to save. They want to save L1 gas. Obviously, it's dropped a lot, but it wasn't even a case of money. They had so much execution that they wanted to do that they physically couldn't do it in one block. In fact, they wanted to do 1.2 billion gas worth of execution. What they were doing before was just queuing it up and waiting really slowly and clogging the chain. It was actually very simple stuff like checking balances, renegotiate, like sending things across and over. So They use steel specifically, basically to compress 40 blocks of execution into one execution proof. And I'll show you how that looks like in terms of a simpler example. And no, that's good, thanks. And it's basically 40 blocks of execution is great, but there actually isn't really much of a limit in how much you can compress into a ZK proof. We've seen in some of our experiments, 50 billion gas, 100 billion gas, and onwards. Of course, it's a design question as well, because you have to think about how your execution actually updates the state on chain, but we'll get into that in a second. Cool, yeah, I just found this TM, lots of blocks. Next slide. So what does steel unlock? The idea is to have an unlimited execution constant gas cost. So obviously the constant gas cost here is just proof verification. And any bits that you add on top in terms of updating state based on that execution. So the price of proving is going to be, and is already probably a tiny fraction of price of on-chain execution. Next slide. And the price of execution proving is a tiny fraction of the price of on-chain execution. Now, the reason I say execution proving is that's what steel is all about, right? So now I can talk about what is steel. So you've understood that it's going to save you some money. It costs about $5 to generate proof and $12 to verify at today's gas costs or whatever. You can compress a lot of execution. So what is steel? So I mentioned this before. Yeah, so steel is you can think of steel as kind of smart contract execution proofs. And to start with smart contract execution proofs, let's break it up a little bit. So we have smart contract execution and proofs. I won't bore you too much with smart contract execution. We're all familiar. You're going to swap something on Uniswap, for example, right? So what's actually happening here is a function is being called. We have some sort of amount in and out, what the address is going to, and some extra call data. Now, this is all exciting, but really what's actually happening here, like obviously we all know why smart contracts are cool, but what's actually happening here is we want to swap something, we've got to check something that exists, basically. Can we swap those two? Does the two address exist? Does it have the correct amount of money, and so on? So basically doing a lot of state checks and then doing some sort of execution based on that. A bit more complicated execution might be like an add liquidity to a liquidity pair. I've used V2 for simplicity, but you get the idea. Cool, so in a normal gist of smart contracts execution without risk zero or any ZKVM or any ZK tech at all, you kind of have an input transaction. So this transaction says, hey, I'm going to call this function. It could be swap, could be add liquidity, whatever. And the smart contract handles the logic and the state, and the EVM handles some sort of execution based on the transaction is the input. We have some sort of like rules and framework for what that input's going to do. The EVM handles it, and the output at the end of the day is a state update. In the state update for a swap, if you go back, the state update for a swap is, hey, this address has this balance now, and this address has a different balance. Okay, now. So what's really important, and why we all love blockchains, is that smart contract execution needs to be verifiable. So it's limited. I'll get onto what these things mean in a moment. So let's start with verifiable. So verifiable is like the reason we have blockchains, and we come to consensus. It has to happen in basically a deterministic way to make sure that nothing goes awry. And we've seen that it is relatively limited, even with our fantastic Scourge, Sludge, Merge, blah 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 blah. Yeah, as we all know, and in very many dramatic ways, people aren't particularly happy with the speed of Ethereum's upgrades. But they've done a good job so far. But still, like EVM improvements here in terms of execution are pretty limited down here. If I can see, obviously there's a lot of EVM upgrades, but they're still a few years away. So how do we get to something a little bit quicker? And that's steel. So I've talked about smart contract execution and proofs. So if you keep that in your head while we talk about VM versus ZKVM, I know everyone's familiar with this, so we'll literally take like 1 second. So a VM is a virtual machine. You take a program and some program inputs, and you create an output. You pass it through that virtual machine, and you can think of it as some sort of complicated basic program, but obviously a virtual machine means a lot of different things these days. In a ZKVM, very similarly, you have a program, some program inputs. This is the program you're trying to prove. And you're going to create some outputs. But crucially, you're also going to generate a proof. So with risk zero ZKVM, you take Rust code, and it can be pretty straightforward in the sense of the ZKVM library handles a lot of boilerplate for you. You pass it through the ZKVM, and ideally what you're looking for is the proof that comes out on the other end. That could be a stalk or a snark. So a little bit more complicated look at that is what we have. I'm going to introduce some terms if you're not familiar, though I'm sure you all are. We have what's called the guest code. It comes from being a guest in the host in the VM scenario. The guest code is compiled to an executable and linkable format, otherwise known as an ELF binary, which we target on RISC-V, and that's the RISC-V big circuits here that handle ZKVM, and you actually get what's called a receipt, and I'll talk about what the receipt is in a little bit. That includes the proof, though. Did we miss one slide if we go back? No? Okay, good. Cool. So we saw this execution without steal, we kind of, the blockchain flow that we're all familiar with. Okay, so let's have a look what happens with steal. So instead of that, we're going to need a little extra step here in order to be able to beef up our execution on chain. We're going to write some sort of steal code in the ZKVM, and I'll show you some steal code. And instead of the execution, the input transaction being kind of like, hey, we want to do some swaps or something, we've kind of separated this a little bit. So before we've had state and logic on chain, we obviously still have state on chain, but you can kind of think of as the logic off chain. It's not necessarily true because we still need to do some logic based on what the steal code says. But actually what's going to happen is you're going to generate proof of this steal code, and once this is ready and generated and you want to use it on chain, the input transaction now is not just calling a function necessarily, but it's actually going to send through in call data the execution proof itself. And basically all the EVM is going to handle is proof verification and the execution for the state update. So we still end up with the same finality state, but we're kind of taking the execution off chain and making sure that it's verifiable in the sense of proving that proof that's generated on chain to make sure that nothing went wrong. Cool. So how does the steal work? Okay, so we have what's called a view call in Solidity. Very straightforward. You want to check a balance or something, and it will return you, for example, you check a balance of a native token or an ERC20 token, and it will return you some sort of basic number, usually in way, right? One of the really long numbers in way, and that's what a view call is. So very similarly, in the ZKVM, you can denote a view call, and you'll understand exactly why we're talking about view calls in a moment. So in the ZKVM, we use alloy macros. Basically just say, hey, I'm interested in this function called balance of. For now, the ZKVM doesn't have any idea of anything else, but basically what alloy is doing here is generating the Rust type bindings for this Solidity Solidity view call. So basically I'm interested in this balance of function. We know that it has an argument of a count, and it's going to return us a uint. Okay, so now we have a little bit more of an interesting slide here. So we have this alloy macro that says, okay, we're interested in balance of. So what are we actually doing in the ZKVM steal code?
Is there a closing bracket missing there? Or?
Probably. I mean, yeah.
It doesn't feel like it would compile.
So you mean here?
Yeah.
So yeah, there is missing. So I mean, I've cleaned it up so that you don't have to see all the annoying imports and stuff. But yeah, you can kind of almost think of this as pseudocode missing like a couple of things, because I'll show the full slide later. Spoken like a true coder, is there a closing bracket missing? Cool. So in the guest program, what we're actually trying to do is say, hey, we are interested in proving that this balance existed at this block, right? So this is the kind of like proof of storage or proof of storage slot. And what that allows you to do is basically basically do some execution based on that value. Once you prove that that value is correct, or returns you a value, you prove that it's correct. I'll get into that, how that's done in a second. Then you can go ahead and do something cool with it on chain. So here in the guest program, we have a couple of steps. It's a lot of code at the moment. I'll actually go through each one in the future slides, so you can go in the next slide. Okay, the code itself is like interesting to talk about, but you can go on the Steal docs and read it in 30 seconds, or you can ask me. But I will go through it in a moment. What's actually interesting in Steal is like, okay, fine, you can denote a view call, like I want to check some sort of balance. Is it actually useful, right? Is it trustworthy? Remember, the ZKVM has no network connection. So how are we interested in some sort of function call from within the ZKVM, right? Like it can't access an RPC node. So how does it know what to do? Well, Steal is the one that sorts this out for us. And actually, we use RAVM within the guest program. So basically, this is all handled for you. At no point do you have to worry about REVM, just the steel syntax, but I'll get into it. Okay, so in the ZK VM, we have a host program and a guest program. Now, I said the guest program does not have network access, but the host does. So you're already probably understanding where we're going with this. The host can call an RPC and can send information to the guest, and the guest can send information back to the host. So, perfect, thank you. What happens is the host calls an RPC and says, hey, I need some information about this balance of function at this contract address, right? It's not, I didn't label it before, but you just put that in as an argument. So, okay, I'm checking a balance of this ERC20 token on this chain, and I need the RPC data. Cool, that's fine. But how can we trust the RPC is going to give us correct data, right? Like how? Because remember, now we're going to use this to do some sort of cool verifiable execution and actually use that on chain. So we're going to make sure that this RPC data is correct to the best of our ability. So we also do an RPC call called eth_getProof. Is anyone familiar with this RPC call? Probably the vlayer guys definitely are. So what this is it returns you a Merkle, basically a Merkle structure in the sense of, okay, here's an RPC, here's the data you requested, and here's all the other data you're going to need in terms of Merkle proof in order to be able to build up that data back to the block root or block hash, right? So basically, here's the data you're interested in, and here's a Merkle proof of the data is included in the block. Now there's an EVM environment that's created. Sorry for the little formatting error there. And what actually happens in the guest program that you don't have to worry about in Steel is the data is handled, so you pass through the data that you want, and also the Merkle proof is verified for you in the sense of now you're in the ZK environment here. So if the Merkle tree is verified within the guest program, you've now when you verify the proof, you're going to also verify that the Merkle tree was correct and the Merkle proof was correct. So that's one step towards, okay, so they gave us a block hash and they gave us a Merkle proof and the data we're interested in, they seem to match. We still have to sort out how that matches on chain though. And finally, it does all the code that you write and carries out the view call. So you can say, hey, I need this balance and I need to do something based on that balance, and then wrap that up in this guest code, and then we're going to do something with that proof on chain. Cool. So in the host program, we have basically you build what's called a provider, and you say, okay, we're going to pass through an RPC URL. I mean, it's a similar provider as if you use like Ethos.js and stuff. It's the Alloy one. Then we're going to create an EVM environment that says, hey, pass through the RPC URL. This is all boilerplate, and I'm trying my best for the boilerplate to be even less words, although Rust has a tendency to be quite verbose. The most interesting line in this host program, this you just copy and paste. The most interesting line in this one, you also can copy and paste, but just change your argument, is hey, I need to call some sort of contract object, and I'm going to give it the argument, which in this case is the contract address, and I'm going to then pass that input into the guest program. This will make a little bit more sense as we go along. Okay, so now we're in the guest program. We're going to read that input that we just got from the host and automatically read some interesting variables, which will be the input in terms of the EthMVM object, the contract, and as you can see, that's an address. Same for the account, so that's the balance, the account balance that we're going to check. Here we're doing it against Sepolia, so there's these things called chain specs. You can look them up on our docs, mainnet, optimism, all those ones are also, you just kind of replace that word there. Then we're actually going to do the contract call from the guest program and say, hey, okay, I want to call this balance of function, and I'm going to take the return, and I'm going to do something against it. So I've called this contract. You can effectively think about this as calling the contract, saying, hey, what's the balance of this address? So this contract is the token contract. What's the balance of this account? Now we're going to say, okay, this execution is going to fail. It's going to panic if the value is not bigger than 1. Now this is our like dummy execution. It's not super exciting. I mean, vlayer does much more exciting stuff with Steel++ type things, but this is just to give you an idea of how it works. Finally, there's this thing called the journal in the ZKVM, which is kind of like where you write your outputs. So anything you want to be public outputs and useful things of your proof. Remember that whenever you verify a proof with the journal, it's going to be, the journal is always going to be checked against the proof. So basically, this is the most important aspects of what you're actually trying to calculate and use in your execution. Okay, so now I've said a lot of words about a lot of stuff, but let's see what it looks like on chain. when we actually take a look at what happens. So this is very, very pseudocode, but we want to do something cool on chain in the contract. And I mentioned that journal right there. We'll get to that in a second. And you pass through a proof in the function arguments or in the call data when you call it. And basically you validate what's the journal data, and you validate a steal commitment, which I'll get to in a second. You verify the proof, and you do something else. So validating the journal data, in the last slide we saw like, okay, we committed the balance to the journal data, right, that we checked, and we can commit anything else. When these are the most important parts of your proof, you always want to validate them. You'll see in a second, in a few slides later, that basically means if your journal data does not match the proof includes the journal data within it, then it won't verify. So you have to make sure that that these are like the most useful like anchors or trust anchors of your proof. Then we have this thing called steal commitment, which I'll get to in a second. Finally, you verify the proof, so you can think about this as, in the last slide we saw like, okay, we check a balance and we assert that it's bigger than 1. And that was the whole execution, which isn't super exciting, but you can do much more than that, right? As we saw with different examples. And then you actually can do something else based on, hey, I've called this function, the proof has been verified. Let's do something now that we know the proof is valid and it's been verified. So yeah, what does this look like in practice on chain? And in code. Cool, so this is without steal. Probably all very familiar with something like this. This is what we just saw in the Rust program. Now, it actually is quite simple in Solidity, because Solidity is quite a simple language, thankfully. So, we have a function to check the balance, and we'll increment some sort of counter if the balance is greater than 1. This is an ERC20 counter example that we use in Res0 for the basic stuff. Again, kind of like that assert we saw bigger than 1, we just have a require statement here as well. So with steal, at first glance in Solidity, it's definitely more complicated. We do a lot more steps. But actually, what's good is that no matter how complicated the execution gets, it pretty much always looks like this. So the execution is offloaded into your Rust program, into your Rust guest program, and you will basically always have this boilerplate of a couple of things, which is, as I mentioned, verifying the journal data. Don't read it too much. You can always ask me after. I'm just getting you the main steps. The verifying, making sure that the token contract is the right address. Here, I've just hard-coded the token contract so that you can only ever basically pass through a proof. We call the proof a seal. It's a bit confusing. I think there's some sort of cryptographic reason for that. Maybe people know that and thing. There's a steal commitment, which we'll get to in a second, the final part of my presentation. And then we will actually verify execution proof itself with Res0's verify contracts that are available in pretty much all our chains. And then once we're done with that, we'll up the counter, right? Similar to what we had in the guest program. So we've seen with different examples like with EigenLayer that you can offload a lot of execution off-chain and still have it verifiably used on-chain, just with using proof verifier in Solidity instead. So the final section is steal commitments, which is a very important part of steal, and actually an interesting just engineering thing in general. So there was this line about that I skipped over, which was like, hey, steal.validate commitment. So first of all, you'll notice that we have a steal Solidity library, which you'll import above. And second of all, you'll notice that we have this function called validate commitment, and actually the commitment is in the journal. Now the steal syntax, the steal boilerplate handles the commitment when it's pushed to the journal. So basically, all you got to do is make sure that it's one of two options. But let me explain on the next slide what it actually does.
What was the image ID?
Oh yeah, good point actually. Yeah, great point. That's great. So the image ID is good question. The image ID is basically when you write a guest program. Yeah, kind of. So there's actually when you run a guest program through the ZKVM, it will generate a kind of a hash. Basically, it's actually hashing the memory state through every point until the end, and kind of a unique identifier of your thing. Now, I appreciate that. The reason that a good question you pointed here is because I haven't forgotten to put in the top. You're the first one to notice that, by the way, so well done. The image ID here, you can only ever send the verifier a proof to verify with the image ID. Now, the reason here is because if I didn't send the image ID, you could pretty much verify any proof and it will come back valid. Now, what you need to do is hard code an image ID into this contract and say, this is the image ID that I'm interested in, because this is the proof that I want to be proving.
But you said something interesting. You said it's a hash of every memory state.
Yeah.
But image ID is per code, not per execution, right?
Say that again.
Image ID is per code, compiled code, right?
Yeah.
Not per execution.
Yeah.
So what does it mean, state of memory?
Oh, it's a very complicated question. I get this question a lot, and no one knows other than Frank, the CTO over Zero, is the answer. Basically, there's a very they're trying the best way to make it deterministic, the image ID, because it has to be. Basically, we want to make sure that there's only one hash for every compilable guest program as much as we can. There's I can give you a link after, but there's a good 30-minute video that I lose myself after 30 seconds that you can watch about every memory step and everything interesting in there. Basically, the ZKVM. Yes, I understand your question, but I can't answer it. Yeah, I'll give you the. Yeah. No, it's in.
I mean, a simple way of thinking about it is a hash of code.
Yes, that's true. Simple way. And it's actually very important because, as I mentioned, like if I didn't have image ID here, it could verify anything. So the image ID has to be hard coded into this contract to say, hey, this contract is only ever interested in the proof that is generated from this specific guest program. And finally, there's this steal commitment part that we're talking about. So in the steal commitment, this is pretty much all boilerplate other than this part, which is the token address that we talked about. In this commitment, we're going to actually have a look at what the commitment does in a second. So next slide. Thank you. So steal retrieves that like state, in this case, a balance of some sort of the balance of the account, of the ERC20 account, at a certain specific block. You can tell it latest block, you can go back. We actually added a new feature to Steal recently called Steal History, which allows you to, before, you could only go back a certain amount of blocks, specifically what I'm explaining in a moment, but now you can go back basically as far as like a year ago in terms of view call state, which I'll explain in a second. So yeah, on chain, we got can you go back one slide? Actually, I haven't finished. Yeah, thank you. Basically, Steal will handle basically the important block data for you. Now, remember in Steal, we said that we verified a Merkle proof from the RPC, and at least that way we know that the block hash that the RPC gave us, the Merkle proof, and the piece of data that we're interested in this case, the token balance, at least they're verified, right? But what happens if I go on chain and realize that block hash was wrong, right? Like maybe the RPC, it's unlikely, but maybe the RPC was really wanting to troll us or something and gave us a malicious thing. It's unlikely, but we still have to make sure that that it does. So now the best way to check is to check against the block hash available on chain. So once we're on chain, we need to make sure that when we verify a steal proof that everything is correct. And in that case, specifically, what we need to check is the block hash available within Solidity's context. That's usually block hash opcode. Block hash only goes back 256 blocks. So that's about 50 minutes at current block times. So what that means is as soon as you generate a steal proof, you have about 50 minutes until it becomes invalid. Because after 50 minutes, if you try and verify the steal proof on chain, it will not have the block hash available to check against the RPC block hash that's been set in the guest program. There is another way to do it on L1 only, since the beacon chain after the merge.
More about an hour, no?
Yeah, maybe if what's the block time now? 12 seconds?
12 seconds.
Yeah, for
per minute, 256, that's 50 something minutes.
Yeah, something like that. Yeah, about an hour, yeah. There is a bit of a longer way to do it. Sorry, excuse me. There's a way that you can do it for about 24 hours. The beacon chain stores the block root for about, it does it in timestamps. So it's about the last 24 hours. So when you write your steal code, you can actually say, hey, I want to use the beacon chain for verifying it. And that will allow you, but it only works on L1, but that will allow you to go back 24 hours in the sense of that your steal proof will still be valid, let's say 24 hours later, max, if you, for some reason, have some sort of latency between the two. So yeah, on chain, oh yeah, so about 50 minutes, maybe an hour, and 24 hours. So I've already explained this whole part. Next slide. Okay, cool, and there's a summary slide. So it's limited, we want it to be verifiable, and I've talked about the verifiable parts of Steal. That's like the Merkle proof, the checking of the information on chain, and making sure that everything is okay. And finally, what Steal is trying to do is offer you ZK smart contract execution for Solidity developers. You can kind of think a lot of the Rust code I showed you, and I can show you more afterwards, is boilerplate. The most interesting part is you kind of just write solidity in that sol macro, and then the steel will handle the rest for you. So realistically, if you don't know steel, if you don't know that much Rust, you can still use steel. Like, it's okay. Most of it's boilerplate. But obviously, once you get to more complex things, obviously knowing Rust is an advantage. Excellent. Cool. So what actually happens as a summary is that there's this like REVM in the guest environment that helps check the Merkle proofs and all this stuff. And the host gets the RPC data, passes through the Merkle proofs to the guest, it just checks them, and we do these on-chain commitment checks as we just talked about. And obviously with the proof verification is also handled on-chain. Cool, that's the end of my presentation. I appreciate that Steel for vlayer, it's probably not for the vlayer people, is probably beginner stuff considering how much you guys are inspired by that, but in general, hopefully people found it useful.